Okay, so this is video example number 2, and in this example we are going to try to incorporate some logic gates into our design. In the previous example, video number 1, we just had a very simple connection from the switch through the FPGA to the LED, and it wasn't really doing anything useful. So in this design, we're going to learn how to incorporate logic gates into our design, and we're going to start with the easiest way to program in Verilog, and that's at the gate level. Now, this is the easiest way to program, but it's not really the most powerful. We'll come to learn other ways of programming in Verilog, especially the behavioral paradigm, which is much more powerful because you can actually describe the function of your design rather than the design itself. Okay, because at the gate level, what you do is you just instantiate the design gate by gate. But of course, as your design becomes more complex, you could end up with hundreds or thousands of logic gates, and then it becomes very difficult to do that manually. But with the behavioral Verilog, you can actually design, you do the design based on the description of what you want the design to do, and then it's up to the compiler to actually find the particular arrangement of logic gates. That's going to come later. For now, let's see if we can design a very simple module in Verilog, which is a simple AND gate. So I'm going to go through the new project wizard again. Be very careful because, as I said several times already, you can go wrong in the new project wizard. You have to follow the steps very carefully. And what I said before is it is good practice. In fact, it's a necessity to create a new folder for every new project. All of your project files then exist within their own folder, and there's no possibility of conflict. So I'm going to call the folder example 2, and I'm going to call my design example new 2, just so it's got a slightly different name to the folder name. So it's an empty project. We don't have any files to add from another project. And we now need to find the code for the FPGA that we're using. So that's going to be this one, EP4C E22 F17C6. This is the code which is on the FPGA. If you haven't got a good eyesight, you can look at the picture on the DE0 Nano user manual. Right, so that's okay. Finish. So we're going to be following the programming design flow once again. So what we need to do first is a design entry. So what I'm going to do is make a new block diagram schematic file so we can basically put our design in here. And I'm going to put my AND gate within a module. It is possible to actually instantiate AND gates directly within the BDF by looking at the logic primitives here. So you can see we've got AND gates. We can put those in the BDF if we want. That's not the most efficient way to do it. It's actually better to use Verilog code to instantiate these gates. So I'm going to go to File, New, Verilog HDL file, and I'm going to create a module. And I'm going to call this module, I'm just going to double check my picture, and module.v. So it's going to be and module. In brackets, we have the inputs and outputs. Of course, there's going to be 2 inputs to the AND gate, and there's going to be 1 output. So we have to define the inputs and outputs explicitly. So in1 and in2 are inputs, and out1 is our output from the AND gate. Now, the next thing we want to do is actually instantiate the AND gate. And the way to do that in Verilog is to use the AND keyword that will instantiate an AND gate, and we give it an instantiation name. So if you do this, this will instantiate an AND gate called AND1. And that instantiation name is important because if you wanted multiple AND gates, you just give them a different instantiation name. So that's how you do it. Now, the way it's done, the convention is the output from the AND gate comes first, and then we have the two inputs, and then semicolon. So hopefully that should instantiate one AND gate within our module. So I'm going to go ahead and save this project. So the module. So I'm going to save the module as end module. Make sure it's going into the root directory of the project, which is example 2. That then appears in the files part of the project navigator. And then, of course, we can right-click and module.v, and we can create a symbol file for current file. So no errors, which is good. So we can double-click, and we can put our module into the design. The next step, of course, is to add the pins. So we need 2 input pins and 1 output pin. And we're going to do something very similar to last time. We're going to have the input pins coming from the dip switches, and we're going to have the output pin go into the LED. So let's give them descriptive names. So I'm going to call this one switch 1. The second one is going to be called switch 2, and the output is going to be called LED 1. So let's save the block. Let's call it block. And now, according to the design flow, we now need to perform analysis and elaboration, making sure block.bdf is the top level entity. So processing, start analysis and elaboration. So again, it's a very simple design, so it shouldn't really take too long. And once that's finished, we can then go to the pin planner and we can populate the pins. So I'm going to say the LED is A15, and then it's M1, so A15, enter, and then it's M1, and switch 2 is T8. If you're not sure where these pin assignments are coming from, you have to look at the user manual for the DE0 Nano, and in this user manual it gives you all of the pin assignments for every possible peripheral, the clocks, the LEDs, the switches, the push buttons. All the pin assignments are included in this user manual, so this is very, very important. So once that's done, we can go File and Close, and then we can compile. Now, when we program the device, what do we expect to happen? Well, it's an AND gate, so we have to look at the truth table for an AND gate. And of course, with an AND gate, if both of the inputs are 1, then the output is 1, otherwise the output is 0. So we're going to see if that actually happens. So again, go to Tools and Programmer. Note that we now have a logic element. So it's actually consuming 1 logic element on our design. And you get kind of a sense of scale of how much we can expand this design before consuming all of the resources on our chip. So let's hit program. So at the moment, M1 and T8 are these two. So if I turn one of them on, nothing. both of them on, so both switches are in the on position, the output becomes 1. If either of those switches are off, the output is 0. Now, we can change this to an OR gate if we want. So if we go back to AND module and we change this to an OR gate using the OR keyword, and then we might as well change the instantiation name as well, even though that's not necessary. Save, create symbol file for current file, update the block, reprogram, and then we can see if this behaves like an OR gate. Of course, with an OR gate, if either of the inputs are 1, the output is going to be 1. If both of the inputs are 1, the output is going to be 1. If both of the inputs are 0, the output is 0. So let's program the device again with the updated design. As we left it last time, one of the inputs is 1, so the output is 1. Both of the inputs are 1, so the output is 1. Now in this case, both of the inputs are 0, so the output is 0. So that's how you make a very simple AND gate or an OR gate within a module. So now we can see we are actually consuming one of the logic elements, and we can start increasing the complexity of this design by incorporating more logic gates, because essentially with digital designs, all they are is a collection of logic gates connected together in a particular way. Of course, to do complicated things, we need more and more logic gates. It gets to a point where it becomes too complex for a human to design these logic gates manually. That's why in future videos we will be looking at behavioral Verilog code, where you actually describe the behavior of the design, and then the compiler has to worry about the arrangement of gates. But in the next one, we're going to look at a more complicated gate level design by incorporating more logic gates in this module.